All right, here we go. This is section 7.6.2. It's the second lesson on factoring polynomials. We're going to start this lesson with an example. It says, use the graph to determine the factored form of y equals x squared minus x minus 2. Now, we have done a lot with the factored form of quadratics. This obviously is a quadratic. We already know how to factor a quadratic. We also already know how to apply the quadratic formula to a quadratic. Both of those techniques would allow us to rewrite this equation in factored form at a slightly different method. And we're looking at it because we're going to apply it to cubic functions on an example later in the lesson. So we're going to graph this equation. We're going to find the roots form. So I have my calculator. I'm going to plug the equation into y1. So we have x squared minus x minus 2. You want to make sure that you have a good window. This is a pretty standard. It would make sense if you hit the zoom button and go down to number 6. That gives you a standard 10 by 10 window, and there's the graph of our quadratic. Now we have to get the roots from this graph. We know the roots are the points where the graph crosses the axis. Well, these roots are actually quite clear. I don't think we need to do a calculation on the calculator. We can see that there is a root at -1 and +2. Our factored form of a quadratic. We're going to plug in our roots, -1 and +2. We know that subtract +1, and we'll keep that as x minus 2. Now what's left is we still have to find out what a equals. We're going to use the y-intercept to plug into this equation to solve for a. And you can check your y-intercept on the graph. It's pretty clear that it's at 0, -2. But if you want to... So let's plug in 0 for x, -2 for y. Simplify it. -2 equals a times 1 times -2. -2 equals -2a. Divide both sides by -2, and a is going to equal 1. Remember that a is our vertical dilation, so this tells us that there is no vertical dilation. Our final answer of y equals 1 times x plus 1 times x minus 2. And that is the same equation now written in factored form. Alright, so as I said before, we've done a lot of work with quadratics, and this graph is a summary of the details of things that we've done so far. And it's showing you the different types of quadratics, the different types of parabolas that you can come up with. In our first graph, right here, we see a parabola that does not touch the x-axis. It doesn't have any x-intercepts, it doesn't have any roots, it doesn't have any zeros, but it might have imaginary zeros, right? It says if the graph of a quadratic function does not intersect the x-axis, then you cannot factor the polynomial using real numbers. However, you can use the quadratic formula to find the complex zeros, a conjugate pair. This is something that we've done already, right? In the second graph, right here, we can see that that parabola does cross the x-intercept. But it doesn't cross the x-intercept at very clear points. Like if you look at that, well, You can't estimate what that number is. You also cannot estimate what that number is. So it says, if the graph of a quadratic function intersects the x-axis, but not at integer or fractional values, then you can use the quadratic formula to find the real zeros. This is also something that we've already done. And then finally, our third graph here, you can see that that parabola crosses the x-axis at 2 points, and they're very clear points. In fact, this is the example we just did. You see that equation? That's the equation we just did on this page, right? So it says there, if the graph of a quadratic function intersects the fractional values, then you can use the x-intercepts to factor. This is often quicker and easier than using the quadratic formula or a rectangle diagram. A rectangle diagram is something the book talked about. It's not something that a strategy that we used. Okay? So what this slide is doing is it's summarizing the various ways that you now know how to find the zeros of a quadratic function. All right, now let's transfer this knowledge to the cubic functions. Now, we talked about cubic functions in the first semester. A cubic function can have a couple different looks, and I'm going to show you these looks in terms of the x-intercepts. A cubic function, in fact, the parent cubic function, looks something like that. And you can see that that cubic function crosses the x-axis one time, right? A cubic function could also look something like this. That cubic function touches the x-axis at 2 points, right? Here and then here. And this is at this point here is actually what we would call a double root, right? So whenever you came up with your roots of the cubic, you always come up with 3, but 2 of them would be the same. Or a cubic function could look like this. And in this case, it has 3 distinct zeros, or roots, or x-intercepts. Now, factoring a cubic is not an easy thing to do. It's not like a quadratic. With a quadratic, we know we could factor it, we could apply the quadratic formula, or we could look at the graph. Cubic functions, much more difficult. There are various ways to go about factoring a cubic, and we'll talk about some more of them. But for today, the first method that we're going to talk about is by graphing it. So we're going to take this cubic function, 4x cubed plus 8x squared minus 36x minus 72, and we're going to graph it. Now that I've entered the equation into y1, I'm going to have to come up with a window that works. I don't know what this cubic function looks like. So I'm going to start out with a standard, or actually, you know what I'm going to do? Yeah, I'm going to start out with a standard window. So I'm going to go zoom 6. Let's see what happens here. Okay. Well, I can get an idea of what this graph looks like. I can see that it's increasing here, then decreasing, and then it's coming back up. So at some point down where we can't see, it's turning around and increasing again. Well, let's adjust the window to get a better look here. I know that I want to see more negative y values. So I'm going to hit the window button. I'm going to go down to my y min, and instead of negative 10, I'm going to make it negative 20. Let's see what happens. Now we'll graph it. Okay, We can see more of the graph, but we still cannot see the bottom where it turns around and comes up. So let's change the window again. Instead of negative 20, let's go negative 40. See what happens here. Oh, okay, still can't see the bottom. Let's go window, negative 80. And this is exactly what you would have to do on your own in order to find the perfect window to see this entire graph. Negative 80 still isn't working for me, so let's go down negative 100. And I'm going to change my Y scale now. Instead of counting by ones, let's count by tens. Now let's see. I'm going to be interested in the same things I was interested when we were looking at that quadratic example. I'm interested in the roots, and I'm going to be interested in the y-intercept. So let's now find what these various roots are. These roots look pretty obvious when you're looking at the graph. Negative 3, negative 2, and positive 3. Let's confirm these by tracing. Trace. Let's type in negative 3 for x, and we should get 0 for y, and we do. Let's plug in negative 2 for x, and we should get 0 for y, and we do. Let's plug in positive 2 for x. Oh, it's not positive 2, it's positive 3, 0. So we know let's start with our equation, R1, R2, R3. We know the roots are negative 2, negative 1, and 3. Okay, so I made a mistake there. It's negative 2, negative 3 in here, not negative 1. All right, so I've gotten my roots from my graph, but of course, I'm going to need to find out what a equals. And just like in the quadratic example, we're going to use the y, plug it in, and then solve for a. So we have to get the y-intercept off of our graph. Well, that's easy to do because the y-intercept always has an x value that equals 0. So my y-intercept is the point 0, negative 72. All right, so let's plug in negative 72 for y, keep our a, and we're going to plug in 0 everywhere else. Notice I changed the minus and negatives to a plus right here and here. Now we're going to solve for a. So we have negative 72 equals a times 2 times 3 times negative 3. Negative 72 equals 2 times 3 is 6. 6 times negative 3 is negative 18. So negative 18a. Divide both sides by negative 18. A equals 4. So now we can write our equation out in factored form. Y equals 4 times x plus 2 times x plus 3 times x minus 3. So what we now have learned is that one way to factor a cubic function is to graph it, find the roots, use the y-intercepts, and then you can write your cubic function in factored form.